Okay, so this is the test review for Chapter 6 through Chapter 9 for the year 2023 to 2024. So looking at test reviews each year, there's different ones, different tweaks to them. But for this year, question number 1 asks you, we have a motor that's going to lift a crate. So we got some sort of a motor here, maybe with a winch on it, okay? And it's got a cable that comes out, maybe goes over a pulley. And we want to lift a crate that's 120 kilograms. We need to lift it a total of 13 meters, so I can load it up on a ship. The motor is rated, has a power rating, so power of 1100 watts. And the question we want to know is how long is it going to take for it to lift this crate? Because the longer it takes, the longer it's going to take to load the ship. So I need to make sure that my motor is rated at a high enough power rating to be able to do this efficiently. And so when we start talking about time and power, the relationship that is evidenced there is that power is equal to work over time, or also commonly used as a change in energy over time. If something gains potential energy, or something gains kinetic energy or loses kinetic energy, then we're going to say that some energy or some work has been done. And so these are kind of synonymous. Work typically will be represented by a change in energy if something speeds up, or changes in potential energy. Not always, but here we see there's a change in potential energy. So we could do this one of two ways. We could talk about work being force times displacement. We talk about how much force does it take to lift the crate, how far does it go. We could also say that there is a clear change in potential energy. As this crate goes higher, it's gaining potential energy. Either one of these is going to be interchangeable. So I'm just going to go ahead and do FD just because it's standard force operations. Power equals force times distance, that's our work, divided by time. Power rating was given as 1100. The force required to lift this crate. In order to lift something, you have to overcome its weight, which means that the force applied must be equal to or greater than mg. If it's equal to mg, then it won't accelerate as it goes up. It'll stay at a constant rate, which is good because we don't want to have this crate flying off the end of the pulley when it gets to the top. We want to have a nice stable ascent. And so we're going to go ahead and use the mass of the crate, which is 120, times gravity, 9.8. That should give us the weight of the crate, times the distance it travels, which is 13 meters, all divided by time. This would just be an old Welcheroo to be able to solve for time. Grab my calculator real quick, turn it on, and it would be 120 times 9.8 times 13, and then it would be 15288 divided by 1100. We do the old Welch root, and we get 13.89. We're going to go ahead and round that out. I think for two sig figs, we're going to round that out as 14 seconds. Okay. Question number 2. We are going to take a crate and we're going to drag it across the ground by applying a force of 310 newtons at a 12-degree incline above the horizontal. So that's 12 degrees. Instead of pulling it straight across the ground, we're using what's comfortable for us. And so maybe you can imagine you're standing there and you're pulling the rope on your shoulder, and you're pulling it along. Okay? And so as we go through that process, we know we're going to pull at a 12-degree incline, and we want the crate to move a distance of 6.3 meters before we stop. Those are all all information given in the problem as we read that. And we're going to go ahead and be asked, how much work does it take to do this? Okay, if I want to do work is defined as F times D. And I cut this off on the last problem because everything was in the same direction, but here it's also times the cosine of theta. That's our formal definition for work, where the direction of force and the direction of displacement, if there's a distinction between them, that theta is the angle between those two the force and displacement vectors. So here the work would equal our force of 310 newtons times the displacement of 6.3 meters times the cosine of the angle between the displacement, which is straight to the right in a horizontal direction, and the force vector, which is 12 degrees above horizontal. So that would be a 12-degree incline. This is a really simple calculation to make. We just throw it in the calculator. 310 times 6.3 times, and I'm going to do the cosine of 12. I'm going to check my mode real quick. I'm in radians, but I want to be in degrees. And press enter. I get 1910 for 2 sig figs. Again, we'll call this 1900. And work is measured as an energy in joules. Okay. Cruising along, question number 3 is our first collision problem. We have object A traveling 3.2 meters per second with a mass of 4.2 kilograms. And we have object B traveling with a velocity of 1.5 meters per second and a mass of 3.8 kilograms. And we want to know what's going to be the exit velocities of the two objects after the collision. Clearly, object A is going to catch up to object B. It's going to hit it, and then what happens after? Which way do each of them head? This is an elastic collision, so there are a couple of equations we have to use. The first is MA VA MB VB equals MA VA MB VB before and after. So the mass of the object A is 4.2 times its velocity before the collision, 3.2, plus the mass of the second object, 3.8, times the velocity of the second object, 1.5. Now the order matters here, the signs matter based on the direction. Notice they are both headed to the right, so they're both positive. This would equal the mass of the first object, 4.2, times its exit velocity, which would be VA2. We don't know what its velocity is after the collision, plus 3.8, the mass of the second object, times its velocity after the collision. So we'll need to do a little simplifying to this equation here in a second. I'm going to stop and come over to the second part of the problem. We also have one equation. These are the two elastic collision formulas. The second one is about the velocities. It is that the velocity of your first object minus the velocity of the second object will equal the difference of the velocities after the collision if the order is reversed. So the 3.2 was VA1. We're going to start with VB2 minus VA2. Notice the order is changed in that subtraction. Okay, this is going to allow me to simplify. Is 1.7 equals VB2 minus VA2. Sorry about the handwriting. And then if I solve for VB2, it would equal 1.7 plus VA2. That is going to work really good for substitution over here on the original problem. Now I'm going to need to do some simplifying and some evaluating. So if we take 4.2 times 3.2 plus 3.8 times 1.5. Whoops, what did I type wrong? Oh, I'm missing the times. 3.8 times 1.5. All right, let's try that. 19.14. All right, so 19.14 equals 4.2 VA2 plus 3.8, and instead of writing VB2, I'm going to write what it's equal to, 1.7 plus VA2. If I do a little distribution and some cleanup, I'm going to get 1914 equals 4.2 VA2 plus 3.8 times 1.7, whoops, is 6.46 plus 3.8 VA2. I'm going to subtract the 6.46 and combine my like terms. I think this becomes 8 VA2 equals 19.14 12.68. If I did that all right, 12.68, and we divide both sides by 8. Divided by 8 gives me 1.585 for 2 sig figs. I'm going to round that to 1.6. So VA2 is 1.6 meters per second, and because it's positive, that is to the right. I also need to know VB2, so I'm going to plug that in for VA2, and 1.7 plus my 1.6 should give me 3.3 meters per second for VB2. And it would also be to the right because it's positive. Okay, so those are our first 3. Let's see. Question number 4. Okay, we're going to do this as a center of mass problem. Okay, and the way that we're going to do this, we're going to take this balancing beam. It's 1 meter long on each side, and we have a center of mass sitting in the middle. So you could think of this as 1 meter here, and think of this as 1 meter here. And we want to put 3 masses. Mass A is 4 kilograms, mass B is 7 kilograms, and mass C is 5 kilograms. We want to put all 3 of these on the balance beam. You are not allowed to put anybody on the fulcrum. Imagine that this has an electric fence right here, okay, with barbed wire on it too. It's bad. Can't put anybody there. You'll kill them, so don't do that. Then I have to figure out where else can I put them. This is open-ended, so there's more than one way to write this problem. But what I'm going to do to just make my life as easy as I can, let's go ahead and put the 7 kilogram guy out on one edge. So I'm going to put the 7 right there. And then I'm going to put the 5, which is the next biggest, okay, over here on the ends. I try to put the 2 biggest guys as far away from each other as I can, and that'll let me work with the single guy in the middle to fit it out. Okay. In order for this to balance, I want the center of mass to be right in the middle, because that will cause there to be no torques or rotations. The center of mass calculation is that you take the mass of an object times its location. So for instance, the mass of object B is 7 kilograms times its location. Now in the word problem, it says specifically to measure everything from the left edge. So this would be considered position 0, this would be considered 1 meter over, and this would be considered 2 meters over. So 7 would be times 0 plus my 5 kilogram box or mass is 2 meters over, plus my 4 kilogram box is at mass is undisclosed. I know that the 4 kilogram is going to go over here somewhere because it's got to be away from the 7, but I don't know how far. And so for me to figure that out, I'm going to leave an unknown there. And the center of mass divides all of these mass times position. They get divided by the total mass. Well, 7 plus 4 plus 5 gives me a total of 16. But where do I want the center of mass? This is really important. I need to know where the center of mass is going to be. I'd like it to be right in the middle. Well, then the position of the center of mass is 1 meter, because I want it to be in the middle of this. So that means that instead of writing position of center of mass, I can actually replace this with a 1. So let's get rid of all that and put a 1 right here. This makes this problem easy to solve. 7 times 0 is obviously 0. I can times the 16 over and get 16 equals 10 plus 4x. Subtract the 10. Sorry, there's where my line should be. 6 equals 4x. If you divide by 4, x will come out to be 1.5. That means that this 4 kilogram mass should be at 1.5 meters. And so we can write ourselves a little note. Okay, 1.5 meters for this guy. For the mass of object B, we're going to put 0 meters. And for the mass of object C, we're going to put it at 2 meters. And that's where we put the 3 masses. Question number 5. Okay, we have a skateboard rolling across the ground at 3.1 meters per second. And someone is going to put their foot down on top of the mass, okay? And they're going to put their weight down on top of the skateboard as it goes by, and their mass is 72 kilograms. The mass of the skateboard is 1.2 kilograms. And the question is, as they combine masses, there's this inelastic collision of sorts. The question is, how fast will everything be moving after the collision? Now, this person who's stepping down, we're going to say that they have a velocity of 0 to begin with. And so if we think of this as an inelastic collision, it's the mass of the first object, 1.2, times its velocity, 3.1, plus the mass of the second object, 72, times its velocity, 0. Those are their individual momentums. But when we add them, the momentum must be conserved. And so we have a combined mass now of 1.2 plus 72 times a new velocity. Because they're traveling together, they'll have the same shared speed. And so if we do a quick calculation, that thing goes away. I believe this is 3.72 equals 73.2 V2. And we do a simple division of 73.2. And V2 is going to come out really small. If we do 3.72 divided by 73.2, 0.051, because we've got to go 2 sig figs, 0.051 meters per second. Not very fast. That 72 kilograms is a lot of mass to be added to a light skateboard. All right, last question. Number 6, how far up vertically, that is, will a disc roll up a specific hill? So we're given this hill, it goes up forever long, however far we need to go. Right here we've got a disc, and it's rolling and moving its way across the ground. Okay? When it gets to its highest point, it will stop moving and only have potential energy. Okay? But down here it is rolling, which means it has kinetic energy. However, it's not just kinetic energy in terms of moving across the ground, which is translational, but it's also kinetic energy as a rotational object because it's rotating and spinning. All right, so there's some information that we have to have. First, these kinetic energies will equal the potential energy at the end. So 1/2 mv squared plus 1/2. The formula for rotational is I omega squared. Those are our befores. Afterwards, we're going to equal mgh. Now, you're given some information. The velocity is 5.9 meters per second. That's the translational speed, not the rotational speed. You're given a mass of 18 kilograms and a radius of 14 centimeters, or 0.14 meters, if you would. Okay, when we start plugging information into this, there is an issue with this stuff right here. I, for a disk, is 1/2 mr squared, and omega is equal to v over r. That allows us to use the translational velocity and radius to have an easy plug-in. Since that's information we already have, great. Now there are ways to simplify this down algebraically to a very easy problem, but for the sake of time, we're just going to plug all these numbers in. The mass is 18 kilograms. Velocity is 5.9 squared. Plus 1/2. For I, I'm going to put 1/2 the mass of the object, which is 18, times its radius, 0.14 squared. So this is just the I right there, the 1/2 18 0.14 squared. That's 1/2 mr squared times omega, which is v 5.9 over the radius of 0.14, but it's omega squared, right? See right there, this is square, so this should be squared, equals mass of 18 times 9.8 times an unknown h. Well, we start typing away. We've got 0.5 times 18, whoops, times 5.9 squared plus 0.5 times 0.5 times 18 times 5 point, times 0.14 squared times 5.9, I'm going to square these individually, squared, divided by 0.14 squared. You could put parentheses around that, square it, or not. We get 469.935, and that needs to divide by, and here I will use parentheses, 18 times 9.8 to get 2.66 or 2.7 meters up the hill. Hopefully this brings up questions that you might want to ask in class and is enough to get you in the right direction. Good luck, and we'll see you in class.